Hello, I'm presenting our paper Energy-Aware Design Methodology for Myocardial Infarction Detection on Low-Power Wearable Devices. My name is Odema, and I'm a second-year PhD student in Computer Engineering at the University of California, Irvine. So let's start first with what is myocardial infarction and what are the solutions that already engage these problems. So as said or mentioned by the CDC, heart disease is one of the leading causes of death in the United States, where one person dies every 36 seconds in the United States from cardiovascular disease, and about 600,000 Americans die from heart disease each year. That's 1 in every 4 deaths. So, one form of this heart disease is myocardial infarction, which is commonly known as a heart attack, and it occurs due to blocked arteries where the oxygen supply and the supply of essential nutrients is blocked to the heart muscle. And the longer that this goes without treatment, the longer the damage that is done to the heart muscle, which instantiates that in the case of myocardial infarction, immediate treatment is required. And it's also characterized by a recurrent nature where 25% of the MI cases are actually recurrent. And there is also a silent nature when 1 out of each 5 heart attacks are silent, which means that the patient is unaware that he is already having a seizure or a heart attack. So all this requires or instantiates a requirement for continuous monitoring. To do this, electrocardiograms are capable of monitoring patients' conditions, where they can detect the MI instance through discrepancies in the patient ECG trace, where as you can see in the picture, normal ECG is kind of smooth, while the MI ECG can experience ripples or different voltage levels and transitions. ECG capabilities furthermore have been incorporated within wearable devices in order to enable continuous monitoring and discard the requirement of having to go to a clinical setup or a routine check in order to assess if you have MI or not. So, regarding the wearable solution with ECG capabilities, it requires that you only have an edge device connected to the patient, and the information or MI data are sent to a fog or cloud, and the physician can keep track of the patient's state. Traditional solution instantiated that the processing would be done in the fog or cloud, where data is sent as raw data directly to the cloud for processing. But however, there was concerns regarding the transmission energy, transmission latency, and privacy concerns. So another approach was to apply edge computing, where the processing would be conducted on the edge device itself, and only the final result would be relayed to the cloud in order to say that the patient has MI or not. However, there were challenges regarding the accuracy efficiency trade-off because of the resource constrained nature of the wearable devices. So ECG can be achieved through multiple LEDs. However, there are also single LED solutions, which are mostly incorporated in the wearable devices because they suit the small form factor of the wearable devices. So previous solutions that incorporated single LED included support vector machine and random forest, and both required a feature extraction process in order to detect accordingly whether the patient has MI or not. However, such process was expensive and required a lot of computation, which may not always be suitable for wearable device. So the next solution was to adapt a convolutional neural network. However, memory which captures features automatically through a sliding window kind of mechanism where you capture features across the trace of the ECG directly without requirement of the process of feature extraction. But there were challenges due to the memory considerations of the convolutional neural network may or may not suit the wearable device. And then the next solution was a binary convolutional neural network, where the weights or parameters of a normal convolutional neural network were transformed into binary form. That reduced a lot of the memory requirements of convolutional neural networks. However, the challenges remained regarding the accuracy and energy efficiency trade-off. So through this paper, we aim to address such challenges by automating the design of BCNNs by proposing a design methodology in order for BCNNs to detect myocardial infarction. So for the proposed design methodology, the goal is to find optimal neural architectures or convolutional neural networks for MI detection. This is done through co-optimizing the accuracy and energy efficiency and by providing an automated design space exploration process. Operational concept that our methodology relies on includes that it performs neural architecture search to find optimal architecture parameters of our model, and it's also platform aware to retrieve the hardware-related measurements directly from the target platform. And it also incorporates multi-objective optimization in order to address the energy and the accuracy requirements both. So, in short, we aim to find an architecture characterized by X which satisfies minimum error and energy function. So, for the input to our methodology or design framework, the user would be required to input what kind of data set, which in this case the myocardial infarction detection data set, and input his search space, which is defined by the neural architecture search parameters, and what kind of constraints he wants to impose on his search space, whether there's a certain value of memory. He doesn't want architectures, the search to go beyond that, for example, to constrain the memory requirements of the target device, and what kind of target platform is going to be used in the actual deployment. So this is the methodology. It's based on multi-objective Bayesian optimization, where each iteration a new candidate is sampled and assessed according to the performance objective, where the model, the architecture or model is trained on the MI dataset, and then its performance on the test set of the MI dataset is finalized and included in the multi-objective Bayesian optimization for the final assessment of that architecture. And then once that is done, its device-related objectives regarding the energy are assessed through deploying the model on the actual target platform and then retrieving the power and latency readings directly from the target platform. And through these two metrics, we get the energy consumption of this architecture on the target device. And that's also associated with that candidate architecture regarding its energy objective function. Now, once these two objective functions are evaluated, they are used to update the search with these new evaluations, and then the multi-objective search would proceed to find more promising architectures to sample. So, in the design methodology, our base template architecture is a binary convolutional neural network where parameter weights are limited to +1 or -1, and only a binary activation function is used to clamp the outputs to 1 or -1. This provides theoretically at least 32 more memory efficiency than standard CNNs, which use floating point representation. And also, binary operations promote energy efficiency because they induce or use bitwise operation. And also, BCNNs are different from the traditional binary neural networks, where they proposed a rearrangement of the layers within the convolutional block to propose further memory savings by using only single floating point temporary throughout the intermediate results calculation phase. To give an example for this, we have a 1D convolutional example where the input length is 6 and the convolutional kernel length is 3, and the output size through this inputs is going to be 2. And we have max pooling of length 2 and stride 2. So in a normal convolutional, this would require 4 floating point temporary in order to store the intermediate results from the convolutional layer itself. However, in the BCNN architecture, the convolutional is conducted through one temporary floating point register where, first of all, the result of the first multiplication is stored in the floating point temporary, and then the stride moves one and calculates the next convolutional calculation, and it's compared directly with the value within the register. Since we incorporate max pooling, then the current value is less than the one in the register, so it's immediately discarded, and we continue working with the value already in the floating point register or temporary register. So this value is directly then done through the max pooling, which is the output. It's goes through the batch normalization and then the binary activation directly before proceeding with the convolutional operation. And this is the value that's actually stored in the memory. So once that is done, the floating point temporary is free to continue calculations where the next convolution proceeds, and you have the current value equal 19. The next value is equal 22, higher than the one already in the floating point temporary, so it replaces it, and then the result of the pool, it is considered as the result of the pooling, and then this already goes through batch normalization and binary activation again, and that is the value that is stored in the actual memory. So regarding the search strategy itself, which is multi-objective Bayesian optimization, it runs for n iteration. First of all, we need each iteration, we select an architecture, evaluate it, and then update the search with the current evaluation. So in a Bayesian optimization, each objective function is represented by a Gaussian process model, and the observed points can be annotated as bn equal xi and yi. Previous evaluations are normally distributed with mean m and covariance k, and as you can see, the actual function is represented by the solid line, and the mean is represented by the dashed line, and the variance is represented by the uncertainty surrounding these two curves. We construct an acquisition function that is analytically available in order to guide the search on where it should select the next candidate architecture for evaluation. The acquisition functions are analytically available, making them much cheaper to evaluate than the actual objective functions. Where the maximizer of such acquisition functions is selected as the next sample point. And this maximizer is based on where there is the highest mean or where there is highest degree of uncertainty in order to explore more interesting points within the search space. Once the point is selected, the objective function associated with it are evaluated. Then, once those objective functions are evaluated, we update the posterior distribution with the new point. And as you can see, the point which was selected has its uncertainty collapsed around it. Then the mean and the covariance are updated. Then a new point is selected where the new acquisition function would render a maximum value. This select, evaluate, update loop progresses for n iterations. The final output from the multi-objective Bayesian optimization would be a Pareto optimal set of architectures. Finally, for our experiments and benchmarking, we first used an MI dataset for LED11 ECG dataset in PTB Diagnostic ECG database, which is from the well-known PhysioNet. We found that in that dataset, the number of MI segments were 7 times the number of that of the normal segments. So in order to balance the dataset, we divided the MI segments into 7 groups, and each group we associated with it the normal ECG segments. And then we performed 10-fold cross-validation for each group. And then the final evaluations are the average metrics across the entire groups. For the training of the models, we set them for 20 epochs. We use the Adam optimizer and learning rate of 0.007, and we use softmax cross entropy as our loss function. For the target devices, we wanted them to be the low power wearable devices like Smartcardia Inu, which use ARM Cortex M3 operating frequency of 32 megahertz and very small kilobytes of RAM and flash with 700 milliampere Henry battery. For our evaluations, we use the EFM32 Leopard Gecko for our experiments because it has similar specification, and it also comes with a power profiler that helped us retrieve power readings easily from that target device. The Bayesian search itself runs on a desktop machine with GeForce 2070 Super GPU NVIDIA. Our search space included variable architecture parameters from the BCNN architecture, like the number of BCNN blocks we want to include, the number of filters for each convolutional layer, the convolutional layer kernel length, the convolutional layer kernel stride, and the max pooling layer kernel length and strides. So for our experiment 1, we wanted to do the multi-objective Bayesian insertion on that search space, but we divided it into 3 child experiments for each BCNN block value. So this is the result, where as you can see the Pareto frontier between the energy and error function, where our goal was to minimize both objectives, and we can make 2 observations out of this sphere. First is that the search is more oriented towards energy. This is obvious by the number of architectures that are explored at low values of the energy objective function, like by pointing downwards towards the vertical y-axis. And the second observation is that the single block architecture dominates the other 2 architectures. So, in order to have more control over the search process, we propose to normalize the objective functions within the search process. It allows biasing the search toward one objective or the other, and then we repeated the experiment. And as you can see, now the explored models are more spread out between the 2 objective functions. So this was done by altering the evaluation within the search framework from the direct evaluation or the exact values to a normalized version of these values. And the constant alpha k indicates how much weight you want to allocate to this certain objective function. Model A is one of the models that we are going to use for the final benchmarking. The final experiment, we wanted to assess and compare the Bayesian search against random search. Experiments were conducted over the 1 BCNN block architecture only. And as you can see, the Bayesian search offers more systematic search, as seen here, while the random search identifies a lot more underperforming candidates because it's not systematic. Another observation is that the frontier of the Bayesian search converges after 100 iterations of the Bayesian search. Like it's almost the same at 100 iterations and 200 iterations. For the final benchmarking, we selected 4 models, A, B, C, and D. 3 of them are oriented towards energy efficiency, while model A offers better accuracy at the expense of some energy consumption. So now we trained for 100 epochs, and as you can see, each model of them took around 3.6 or required 3.6 kilobytes of RAM and 19.2 kilobytes of flash. We compared it against the original BCNN architecture, and in terms of MAC operations, accuracy, and energy efficiency. MAC operations are bitwise because of the nature of the BCNN architecture. And as you can see, the model A, for a small value or a small decrease in the error, it requires a lot more energy consumption. And for example, model D, for a more energy efficient architecture, it takes around 1.04 the amount of error that was induced by the original BCNN. So we can conclude that energy efficiency is more affected by architectural choices than accuracy for the BCNN architecture. And we also see that model D is much more energy efficient than the baseline for 1.04 increase in the error. We compare against the other previous wearable solution, SVM, RF, and the original BCNN, according to the metrics of accuracy, sensitivity, and specificity, where TP is the true positive, TN is the true negative, and PNN are the total positive and negative values in the dataset. Both solutions are re-implemented on the EFM32. Device-related measurements are validated over 2 power modes. As you can see, Model A achieves the best accuracy, sensitivity, and specificity values across the entire works or the entire wearable solutions. And we can see that Model D is the most energy efficient model or architecture. So, sum up our presentation, we presented a MOBO-based NAS methodology. MOBO stands for Multi-Objective Bayesian Optimization, to automate the design space exploration of efficient CNNs for myocardial infarction detection on wearable devices. A search space of variants of binary convolutional neural network architectures is constructed to find efficient architectures for wearable devices. One of our explored models, Model A, achieved 91.22% accuracy, which is the highest for MI detection on wearable devices, while another model is 8.26 times more energy efficient than the baseline BCNN, while maintaining a comparable accuracy to the state-of-the-art wearable solutions. Thank you for listening to my talk.